Okay, so this was the introduction of kind of basic NDN concepts, and what I'm going to continue is assuming you can communicate with the names, like you can express the name of the data to the network, and network will figure out how to get this data back. Now we need to talk about the naming, because you have to name every basic piece of content that you're communicating with, but there is also aspect of security. The question just what we highlighted was in IP model or TCP IP model, we're trying to secure the connection. So that's kind of the basic model. So as long as we can set up a connection, as long as we can set up this connection, and while this connection is alive, we have secure communication. It doesn't really matter what we're communicating within this connection, but we kind of make an assumption of security. With the previous conversation, what Professor Zhang was talking about is we don't actually introduce the concept of a connection. I mean, technically, we can introduce that if we really want to, but the granularity that we're working with is a data packet, or like data by itself. So therefore, the conversation here is we need to secure individual data items in this network. And for illustration purposes, we'll try to use the file transfer application within notional tactical environment. And what from the security perspective, what we're trying to achieve here is that files must come from the right people. I mean, they have to be authorized to publish those data. Files needs to have the confidentiality properties, so not just everybody can read the file produced by the right people. And in some cases, you also want to kind of hide the metadata. So because now with conversing in terms of names that we're requesting that we're given to the network, but we not necessarily want to expose exactly what we're asking for, because it also has some small implications. The whole point of security that we're kind of working with is the fact that we're basing everything on data authenticity. So that's kind of the basic stuff. Unless we know what we're communicating with is this data pieces actually came from the place that we're trusting, then there's no more kind of conversation. But then we can, on top of that, we can build a confidentiality part, and on top of that, we can also build the name privacy if the application requires. Okay, so as I said, everything is about naming in this environment, and specifically, you have to think about multiple levels of naming. So first of all, in the file transfer application, the basic concept that you have to think about is names of the files. So the ones that you're basically requesting from the network. But that's not it. Because on top of the network, there is also concept of keys. Like in the HTTPS environment, we have kind of those magical certificates, but those magical certificates in HTTPS technically don't have their own names. You cannot request them. You cannot go to the web browser and just, oh, what is this certificate for the google.com? So there's no such ability to request. When you establish TLS connection, you've been given some set of certificates, and you just trust that those are correct. In NDN environment, because everything is individual data piece, you actually have ability to name stuff, and kind of as I will try to show you, there's extra stuff that you can do on top of that. In addition to just naming the keys, there's also concept of policies, and I'll talk about this as part of the trust schema. And for the encryption case, so that's to implement the confidentiality, there's also some kind of thinking needs to be involved in order to give some meaningful names. Given all these names, so what the application designer, what application just needs to do is simply start fetching data, like express an interest for the data, and just relying on the fact that network will try its best to retrieve the data. It's still kind of responsibility to the final application to actually make sure that data be retrieved. So if you may need to re-express, may try different interfaces if you really want to, but the network will try its best to figure out where the data is, will try to internally potentially discover routes, and kind of if data cannot be retrieved in some offline fashion, so it's kind of it was produced at some point, cached a couple of times, and re-requested 5 minutes or 5 seconds later, that will be the business of the network to retrieve this data. But get back to the name. So that's one of the examples how you can name files, and there's nothing special. So you can just kind of some form of a prefix that can be used in the same way IP prefixes are used, like basically to guide direction of this location. So it can be, in the simplest case, identification of the network, like some /att or slash something, or it can also be some form of a geographical prefix. So if our file transfer application in this notional environment has a geo component, so we can have the prefix that literally say, oh, the field on the right or the field on the left, or so on and so on. Then there's a few more components that are actually quite important. So the first one that you see is actually application name. In IP, we have concept of transfer protocols, and the transfer protocol have the port numbers, and basically the operating system is using those port numbers to direct the request, to direct this packet to a specific application. In NDN, we actually don't need to do that, because we are working on in terms of names, and name everything. And if you receive a name that identified, oh, this is the name identifying the data for the file transfer application, then in order to retrieve this request for the data, the application simply need to register this app/files prefix, and that's it. So that's basically name is acting as a transport layer demultiplexing. And further part of the naming in this example is just some form of application data. So you just need to create a structure that really needed for the application to identify the data, identify the specific, very granular, unique name. So kind of basically you have to go down to the segment, down to the version of the specific segment of the data, because every piece of data that we publish in an NDN is basically unique and immutable. The name, in some sense, it's very similar to HTTP URLs, or URIs in this case, with the one slight difference that we don't really have a separation between the main and the path, because really from different perspectives of the network, this part can vary. So in some part of the universe of the network, you can effectively demultiplex or direct this interest only using apps prefix. In some part of the network, you can use two more components and and some further. So it's easily do some form of load balancing if you really want to, and kind of structure the network as you need. Data authentication. So this is the fundamental piece of NDN. So what we're trying to do is with the data authentication is build in authentication properties directly into the data. So kind of in a trivial form, in kind of the most kind of optimistic form, there is a signature associated with every single data packet. So you produce the content, you sign it, you embed this signature with the packet. So that's kind of the fundamental property. But there's just only kind of third of the story. Because you also need to identify what the key is needed to verify the signature. So basically identify some form of a private key. And on top of that, what you can do is simply publish the public key as a data packet. So simply this is what the second step of the process is. And that now same piece of data. It has a name, it has a content that happened to be public key, maybe some additional meta information about the validity of this this data packet. And it can also be assigned further. So this is kind of basically creating a chain, but we're always talking in terms of the data packets. So we kind of 1, 2, 3, 4, and it doesn't really matter how many kind of levels we can do. As long as we reach at some point the trust anchor that Lisha was talking about, then we can verify this chain and ensure that yes, this data is correct. So, for example, we can have different types of keys associated and different types of hierarchies of the keys created in this environment. For example, we can have a key for the soldier. We can have key a little bit on higher level for mission. We can for the base environment. That if you go down, but we also can go up and say, oh, there's a key for user for a specific application, for user-specific application instance of the application. So basically, we can create any amount of hierarchy if we desire to limit exposure of the keys, because the less we use the keys, the less the keys is exposed to the universe, then the less problematic we have. Okay, now back to the asterisk. Yes, we can build this trust chain, certificate chain, and we can do the verification when we receive the packet if we hit the trust anchor. But one kind of obvious concept is not all the keys are the same, like they don't have exactly the same power. So in this specific case, if it's assigned by soldier key, then it's fine. But somehow if the same data is signed with completely arbitrary key that may or may not got to the point of the trust anchor, that doesn't necessarily mean the right thing. In this, in a very trivial example, that's obviously that this is completely bogus data because it's signed by the Heisenberg key. But in some cases, it can be the right data, the key is signed, but it's signed by the user that's not supposed to sign this data. So that's kind of a basic assumption. And what we're trying to do with NDN, like as part of the NDN picture, we're trying to actually utilize the naming of the data and naming of the key. And again, naming of the key that signed the key, and so forth and so on. And what we can do, we can actually try to leverage in many, many different ways. So somehow, okay, let me just open. So for example, we can put a restriction that the next level key must have certain component, like certain geographical component, certain kind of person, like identification component of the soldier, for example, type of the application, or even like a temporal information, like a date, time, and so forth. So with this, we can actually say, okay, so now we have a data that produces a certain period of time by certain entity for the certain mission and so forth, then this data must be signed by a key that has those components. And the key itself needs to be authorized by such and such components further. So if I kind of redraw the picture a little bit more formally, I can just define, again, this is just one of the examples how you can define this name structure. But basically, in this environment, some form of apps becomes the local trust anchor for this specific set of apps. Then there is some keys for the specific missions, like for the Area 1, Area 2, and so forth. We can have soldiers associated. We can have soldiers within the mission, without the mission. So this is kind of only our imagination limits what we can invent here. And one additional thing, as Alicia was pointed out, kind of people not designed to manage crypto keys, so that's true. And with the structure, it's become a little bit less problematic because we have name, we can kind of now manage keys based on names. But even with this structure, we still need a little bit more of automation, and meaning all this policy that I just discussed, like some keys, some components here and there needs to match and doesn't need to match, it needs to be expressed in some automated form. Today we actually don't have this environment. So today, kind of if you kind of remember what we do in HTTPS, we have some similarity to this environment where when you go to the website, it presents you a certificate, there is a common name in certificate, and you have to match it. So that's kind of the only basically rule that embedded in the browser is to match the common name to the name you're going. And in here, we're communicating with individual data pieces, so in individual data packets. So we kind of actually go to the next level of matching, and we can match everything to each other, like name of the data, name of the parent key to the parent or grandparent key, and so forth and so on. And for this purpose, for the purpose of automation, we actually invented a couple of languages. It's in a simple form, actually in different type of the languages. This is just one example where you can express that some form of a policy that's saying basically it requires matching of certain components of the name of the data and the name of the keys, and kind of going down, down, down back to the trust anchor. One interesting aspect of this exercise is the fact that some part, so this upper part of the policy, is actually fixed for everything. So there's no kind of specifics to the application, specifics to the environment. There is a specifics to the application that in this environment, in this application, we want to have a prefix and matching of the components in a certain way. And to specialize this rule, like, or this policy to this specific environment, to simply define the kind of different trust anchor. And you deploy it for the one mission, you specify one trust anchor, you deploy for a different mission, you specify a different trust anchor, and those completely independent. It's like they're not going to be even interfering with each other anymore. And with having this formally defined trust anchor, you can actually easily implement any type of verification that is secure in terms of the cryptography, because everything will be verified cryptographically, plus it's secure in terms of policy. Because it will literally follow the policy, follow the crypto mechanics for the policy. So that's one part. But there's also a side part of actually creating the data. because it's actually the biggest problem in this environment, because to create the data you have to sign, and you have to have a key, and kind of you have to have a key that satisfies the policy. So that's actually the other side that we're working on, kind of having this automaton of signing to actually generate the proper signatures, and if it's missing the key, like go to a special system that we call NDN cert to request the keys, and they will be issued the keys if they're authorized in some way. Like there is some set of out-of-bound challenges that needs to be satisfied in order to do that. Okay. So that was authenticity. So with authenticity, we can automate to the level that we can, given the data, we can easily verify it, like using just automation. Using this automata to verify using trust schema policy. And using the same policy, we can actually sign the data. For confidentiality, the problem, kind of actually the next level, is you actually want to also have the encryption keys and somehow manage those encryption keys to be available or be disseminated to the guys who are authorized to decrypt the data. The process is quite complex, and I'm not sure whether we'll be able to follow, but okay, there are multiple ways of accomplishing the problem, and one of the solutions that we're working on is a name-based access control, where we try to leverage, again, naming in order to this automation of a dissemination or sharing of the symmetric keys. And in this environment, what we have is we have a symmetric key that actually used to encrypt the data, and then we have a pair of a key encryption key, key decryption key. So key encryption key basically encrypting the symmetric key, and we need to disseminate key decryption key to anybody who is authorized to actually decrypt the data. And when you got the data, you see what kind of encryption key was used, and you're trying to figure out how you can fetch this key decryption key. So that's kind of a basic highlight, and I'll give you hopefully a few highlights with examples how to get that. So anyhow, look, in the system, I mean, normally we have producers and consumers in some way. In addition to just consumer producers, you need to have some logic, at the very least, logical entity that grants access. So in this environment, some form of access manager at the base that decided that certain soldiers, certain UVs I should be able to access to certain data sets. And what producers do in this environment, they produce certain amount of data. And as part of the configurations, part of kind of logical definition of when they kind of being deployed, they're saying this set of data must be kind of disseminated using this policy. And I'm keeping the word use this and that, but they're actually specific, and we can use names to express the policies themselves. And so when you create the data, you kind of encrypt it with a symmetric key, and then you trying to figure out which encryption key needs to be used to encrypt the key. So, okay, so there's a lot of encryption involved, but I hope you're still following me. And on the decryption side is simply you're trying to, first of all, retrieve the data, because that's what the NDN is about. And in that data, you're actually looking at the information of that it's encrypted. There's information about this, the encryption key that was the symmetric encryption key, and you fetch that one. That one will be in encrypted form, and that also identify which encryption key was used to encrypt the encryption key. There is a lot of dependency, but we'll get in the next slide. I hope it will be quite simple. Oh, simpler, I wouldn't say simpler. Okay, so for the policies. So the policy basically is about the naming of the encryption and decryption keys. So one needs to be given to the producer's encryption key. The other one needs to be given to consumers, like the one that needs to decrypt. And depending on what kind of granularity of the data control we have, we can give different keys. So for example, in this case, we have authority kind of application MIC, and it has, in this case, defined several granularities for the control, like some files about the ships, some files about troops, and some files about something else. And any data that's been produced that can be assigned to be subject of that specific policy. It can be inferred from the name itself and the matching the data, so this is still ongoing work, how exactly is to express it. Or it can be literally manually configured that this specific data must obey this specific policy. So that's it. That's what we have as part of the policy management. So it's everything done using names. On the data producer side, again, you produce the data, you fetch the policy that kind of requests the policy, meaning you request the encryption key by the name that's been configured, and then this is how you know how you can encrypt the data, because you produce the data, you have just generated some random symmetric key, and then encrypted that symmetric key using policy key. That's it. On the data consumer side, the actual process is even more simpler, because you get the data. Where's our data? So data is just application name that it's outside the system. From the data, you can infer, you can literally see what's the name of the encryption key. And naming encryption key has an interesting concept. It's actually okay, I actually didn't see it, didn't show you, but it highlights what is the encryption key was used to produce that symmetric key. When you retrieve the data, that key would indicate that it was encrypted by the policy key. So it literally would have apps, files, soldiers, key, something, information associated afterwards. And you can basically convert this back to retrieve the key decryption key. And in this case, you're trying to request key decryption key that was specifically encrypted for you, because you know your own name, you know what the name of the supposed to be policy key decryption key. You combine these two parts, you express this interest, and if you authorized, you will have this kind of data packet available. And then you will be able to decrypt it, you'll be able to decrypt the symmetric key, and you will be able to decrypt the data. So that's kind of a little bit long process, but it's quite straightforward. One interesting aspect of this long process is you don't have to be, like, none of the entities in the system have to be online at the same time. The policy can be granted way ahead of time. The data can be encrypted and published at some also way ahead of time, after policy is being generated, though. And when you get in the data, you just need to fetch the kind of individual pieces, the data itself, the keys, encryption keys, decryption keys, from the system, hopefully cached in some way. So like every step of this process actually highlights the importance of NDN, that you just express interest and you get the data back. And where exactly this data located, where is data being published, it doesn't actually matter. It doesn't have to be the original guide. It doesn't actually be online or at the same time. It's kind of, and the temporal effect is quite interesting. Okay, so another part is name privacy. So name privacy is the one that I was highlighting, the fact that you don't really always want to expose what you're asking. I mean, normally even in the notional environment, we will be working on top of the secure channels, but even if you're working on top of the secure channels, you still don't want the intermediaries necessarily know what exactly you're talking about. And what you can do, you can actually do some form of various forms of obfuscation. First of all, you can obfuscate the prefix into some high-level prefix, and you can obfuscate the suffixes of the name to something else with a few special considerations. So you still want to have ability to direct the request towards the data or the potential location of the data. So you have to be mindful about what kind of a mechanism you actually do the obfuscation. Like how many components, whether you can suppress everything, not suppress everything, whether you still have the concept of some obfuscated name of the application for the demultiplexing purposes or not, and so forth and so on. So we kind of try to explore different granularities of kind of encryption, like what kind of simple encryption you can do. Either you can hide all the components, you expose some components, and so forth and so on. And all of them have different, basically, trade-offs. So one of the simplest ways you can do is simply obfuscate each individual component. You have basically, if you request send a file, by obfuscating individual component of the big name, you basically will hide what you're asking. But still, you'll be able to expose in some form of that you're asking about something like an inconsistent way. And kind of, if you do some form of AI that somebody already talked during this conference, you potentially can expose or like infer maybe not exactly what have been asked, but rather some information or some meta information about the requests. So that's kind of one of the trade-offs. Like it's a good from the perspective of caching, because now it's still kind of forwarding, because you're asking for that kind of random name that has multiple components. That data that be returned can be cached in this form and be reused in different places. So, but from the inference perspective, it's not that great. If you go the opposite direction, simply obfuscating the complete name into the one component. So now you have, like, there was a very rigid structure, or not rigid, the opposite rigid, flexible structure of the name that was used by the network to forward it, to demultiplex, and now you can just collapse everything into one, basically removing a lot of elements. So now you kind of, you're losing potentially some of the caching, potentially demultiplexing ability, and so forth. It brings a lot of privacy, because now it's really hard to infer what you're asking, but not too friendly. So there was a solution that we explored, kind of trying to combine, like, to do a little bit of smart thing, try to compress things, but not completely, like keeping some parts of the prefix for the purpose of networking and demultiplexing, and some parts of to try to hide as much as possible. And if I just simply reflect to what I was showing in the beginning, like for example in this name, basically the part that is useful for networking purposes is the first one. Like we kind of assumed the main part of the URL, even though I mentioned that it's flexible in NDN, but using the encryption, we kind of impose an additional restriction, basically. Then the demultiplexing, you still want to identify some form of application in whatever form, encrypted, not kind of obfuscated, not obfuscated. But the rest, if we're kind of talking about this request going to the host to demultiplex to the application and trying to figure out what to do inside the application, technically the rest is kind of business of the application, and that doesn't need to be exposed in whatever, how many components there, doesn't need to be exposed to anywhere. So it can be easily kind of compressed in some form. So that's kind of the very, very high level highlights of the solution that we tried to explore. I didn't give you too much details, but just to highlight, there's an important part of naming, that if you naming gives you a lot of capability, but if you break a little bit naming, then you may lose some of the abilities of name data networking. And just a few final words about this. So in NDN, we're trying to focus on data rather than individual channels. Again, if you have ability to do to have the two entities or two or more entities communicating at the same time, you still can introduce the concept of some form of a session, point-to-point, multi-point, and do something better than just data-centric security. But that's a fundamental part. And naming is quite a bit universal, as it allows you to kind of try to build a policy for data authenticity. It allows you to build a kind of system to disseminate keys for the encryption purposes, but it also have issues with the privacy, or name privacy exposing some form of a metadata.
I just wanted to comment on this real quick. So the thing that is missed in translation here is that NDN was, there's real interest, and there's actually a big effort that is going on at DARPA to leverage it for permanent share. So one of the issues that they came across when they looked at it was, okay, so it gives me the resiliency, it's good. You can encrypt the data and all that, but hold on, wait a minute, that name that describes the data is all the way up in the clear. So how can and even if I encrypt the data, your name is up in the clear, and you're using that to wrap, so we can't really hide that, right? Your IP addresses have to be exposed so that you can wrap. The same with NDN, the names have to be exposed so that you can wrap. So some of this effort was trying to look at how do we actually provide some security for the name itself? And I think what Alex was trying to go across was some of the options that were explored, so that you can still have the granularity of the name, but not necessarily exposure.